Hi folks, welcome back to the video. Maria again. And yes, in this video, we'll keep talking about light diffraction and light scattering for particle sizing. Just a short revision. In the last video, we talked about the essence behind all this, which is to understand light. So we want to understand light for the scope of this presentation as an electromagnetic wave, which is really an oscillating electromagnetic field that's propagate in the direction of the wave. And then we cover the phenomena. The first one is diffraction. So diffraction really is wave superposition as the high point meets the low point, then it cancels out. So it appears to be a dark spot in terms of light diffraction, and really light passing through an opaque particle is the negative of light passing through a single slit. That's how it works mathematically. Okay, light diffraction, then light scattering is the opposite because light needs to propagate through this particle, interact with its electron cloud, and then this electron cloud generates an internal oscillating field, which becomes the scattered light. Of course, it gets out at a different angle. What angle is it? That's what we're gonna go through today. Okay, now let's continue with theories. Since we just finished talking about light scattering, let's start here. Oh, by the way, I drew some lines linking two ideas together. Yeah, basically that's the reason. So let's start with Rayleigh scattering then. Rayleigh scattering is a theory or like a set of mathematical equations that describe the phenomenon that light pass through and interact with the electron cloud of this matter and then get out. There are two conditions to use Rayleigh scattering. The first one is that the size of the particle needs to be small enough, smaller than the wavelengths divided by 10, because we want to make sure there's no diffraction effect. So basically no wave superposition. So when the particle is small enough, the distance is too small, so it doesn't allow wave superposition, right? Okay, so the second condition is that the particle needs to be optically soft, meaning there's only refraction. Right. So as a result of Rayleigh scattering, the scattered light intensity is proportional to the radius to the 6th power divided by the wavelength to the 4th power. And this really explains why the sky is blue. Okay, let's just shortly talk about why the sky is blue then. So really when we are looking at the sky and we see blue, meaning there's something there, because if there's nothing, like the vacuum, it appears to be completely black. And once we see something, meaning there is something, and we see the sky is blue, then what do we see? Okay, 5 seconds. Think about this question. So what we see are air molecules. And why we see the air molecules? Because they scatter light. And then why do they scatter blue light? Because as you can see here, the smaller the wavelength, the stronger the scattered intensity, meaning like red lights, they tend to pass through the air molecules from the sky and reach the earth without being scattered too much. But the blue light is trapped here, scattered by all the air molecules. Then the question we always ask is why it's not purple. The portion of purple light is a lot smaller as compared to the portion of blue light, and that's why the sky is blue. Yes. So what the point that I want to make here is like the next time when you look at the sky and you see blue, it's really the air molecule wants to say that don't forget that we exist, because like we don't feel them right here, the light, the air, but like once you look into the sky, like you see them right there. It's the air molecules. Okay, so that's Rayleigh scattering. is a Fraunhofer diffraction. So Fraunhofer diffraction directly described diffraction. Actually, no matter is mechanical diffraction or light diffraction, because yeah, as I said, it follows the same principle, which is wave superposition. So the wave here and here at this point, they should cancel out to be able to create a dark spot here. Yeah, so that's the basic idea. We've all learned it in schools. So there are two conditions to use Fraunhofer diffraction. The first one is that the size of the particle should be large enough, larger than 40 times the wavelength, because it allows wave superposition. What I mean by that is that if the slit is too small, then the distance doesn't allow wave superposition, right? There's no distance to generate this different high and low spot in waves to create the patterns. I think this idea is clear enough. And the second condition is that the particle needs to be optically opaque, which means it can only absorb and reflect light. So why? So mathematically, light passing through a particle equals to the negative of light passing through a single slit. And to have this mathematically correct, we need to make sure the light is opaque. Otherwise, it's pretty obvious. Okay, now is the superstar, me theory. So as you can see here, I drew lines pointing me theory to both diffraction and scattering because it covers both and the range in between, and which is the majority of things that exist. So that's why we use me theory, and that's why it's a superstar. It covers all sizes from molecules to galaxies, and it covers all optical property, and that's why you need to input the refractive index to use the me theory. And Fraunhofer diffraction and Rayleigh scattering are really just approximations of the Me's complete solution. And the really amazing thing about me theory is that the instant light, once it hit the particle and interact with the particle, the scattered light getting out of this particle is angular dependence, angular dependent. And this angular dependence is the key here. It's what we use like in a type of technologies to measure particle size. So the light doesn't want to get out this direction, it really prefer to get out just in those directions. Like, how amazing is that? Okay, so just to talk a little bit more about the angular dependence, I want to introduce to you this plot. So the y-axis is the normalized scattering per particle. The x-axis is the diameter. And the different colors of lines is the different detecting angle, like which angle we're observing this scattered light. For example, this blue line here is 173, meaning this is the instant light, and then we are getting the scattered light at this direction, pretty much like backward. Also like 90-degree like this, 45 like that. So the highest point, meaning this diameter at this angle has the highest sensitivity, I would say. At least that's my understanding of it. Okay, so, and also what I want to point it out is this Rayleigh scattering regime. So when the particle gets smaller and smaller, there's less and less angular dependence. And here, like for example, 100 nanometer, you can barely see the angular dependence anymore. You can say that detector is sensitive enough, you can still tell, but like when it gets to like 10 nanometers, there's really no way to see the angular dependence because there's none anymore. Okay, what did I? Okay, so then it hits the lower limits and enters into the Rayleigh scattering regime. Okay, so that's the me theory. And as I said, the technologies are based on the theories. It's how the theories apply to solve real life problems. And here, let's start with LD, meaning laser diffraction. Um, okay, let's talk about the terminology laser diffraction. I put the quotation marks here because we still call this technology laser diffraction, I think, for historical reasons, because rigorously speaking, it's not diffraction. As we just said, diffraction is wave superposition, and it needs the particle to be opaque. It's really talking about Fraunhofer diffraction, but it's not the case because what we use here is the me-complete theory. And really, what we use here in this category of technology is the angular dependence. Um, so it's not rigorous to still call it laser diffraction, but we just do due to historical reasons. That's just a comment that I would like to make. But I definitely don't want to confuse you. So key point, take home point is that when you see laser diffraction, we are really talking about the angular dependence of the scattered light getting out of this particle or passing through this particle. And for the majority of cases, we use the complete me solution. We still have the Fraunhofer how to say calculation method inside the software, but for the majority of the cases, we use me complete solution. Okay, so the idea is pretty simple then. So this two graph shows what you usually find in this type of technology, and the detectors are located at different angles to detect the angular dependence of the scattered light. In our master sizer, we have a red laser. We also have a blue laser because blue laser has a shorter wavelength, so it's better to detect smaller particles. So here's is the size range to be detected with laser diffraction. So yeah, in the middle, of course, we use the angular dependence to detect the particle size. At the lower limit, yeah, just to remind you of this plot, we hit the Rayleigh scattering and there's really no angular dependence anymore in terms of the scattered light. So we couldn't use angular dependence to calculate particle size anymore. And then what do we use? We have dynamic light scattering and static light scattering that I'll talk about later. So move on to the large limit, the biggest particle we can detect using this technology. So why we hit the upper limit? It's really because yes, as I said, light passing through a particle, opaque particle, equals to the negative of light passing through a single slit. As you can imagine, when the slit gets too wide, the majority of the light will just hit the center and there's no way to see the patterns over there. And you couldn't even block the center because that became a double slit experiment, is not measuring the particle size anymore. So that's the range of particle size that works well with laser diffraction. It's really somewhere in between. And the upper limit is a pretty comparatively easier to solve because when the particle is large enough, we can it become visible. Microscope would work perfectly, I think. And at the lower limit is really the headache. It's really hard to see with the laser diffraction, which means the angular dependence, or microscope is definitely like harder. So what do we use them? That is dynamic light scattering. Alright, that's enough for this video. I will talk about DLS, which means dynamic light scattering, in the next video, and see you next time. Bye bye.